right. Good morning. Good morning, everyone. Happy Wednesday. Happy block 5, where we're at right now, block 5. After this block, we're a quarter of the way done with our training. Time flies. Today, block 5 and block 6, especially block 6. So this afternoon, my favorite part of the class to teach. It's really, really, really exciting how quickly we build skill here and can do some really cool, neat things in today's lessons. So I'm pretty excited about that. Couple quick things from previous days, some logistical things to chat about real quick. I have, as of this morning, all of the block 1s and 2 submissions that were turned in have been graded, looked at, whatever. If you haven't turned it in yet, obviously I haven't graded it. So when you go to turn in your next blocks, your 3s, your 4s, etc., when you're getting those done, keep an eye on whether it says completed or revision required. Okay. If you see revision required, you should be able to click on it, and I will have uploaded another file, and I should give you a little direction like, hey, you missed this. This is the wrong picture, whatever. Don't get consumed with it and be like, I can't do the lesson today because I got to fix this thing, crash that. It's okay. Relax. Just get to it when you can get to it. But just keep an eye out for that as you go. I've had in the past participants on the last day of training, they had like 9 revisions required. They're like, what? I didn't know. So just keep an eye on that as we go. Make sure that you're fixing those things when they happen. Okay. When I was looking at block 2s, I noticed something on 114 with a lot of you, and I wanted to chat about it real quick. Okay. So on 114, which again, I know you haven't memorized all these numbers yet. So 114 was the resistor color code and the capacitor activity. This is 114. And generally speaking, you guys did pretty well on it. You had your color codes figured out for resistors, okay, and all that. But there was a lot of different answers in this section. And partially, I think that's due to this little block of text right here. So this little block of text says, note, there is no absolute rule for what determines which units to use to state the value of a capacitor. I find that to be a debatable statement. I mean, there's no absolute rules on most things, but why wouldn't you use engineering notation, right? It says generally capacitor values are expressed as microfarads and picofarads. True. In general, express the value as microfarads or picofarads to minimize the number of significant digits. Now, again, I'm no chemist or other person that loves significant figures, but I'm pretty sure changing the unit does not change the number of significant figures. So I don't buy that rationale for using microfarads or picofarads. Like it doesn't change the number of significant figures. If you write down that something has 20,000 versus 20, it's still the same number of significant figures. So anywho, I didn't mark any of these revision required, just so you know, and any of the capacitor stuff. So if you wrote what I'm about to say, you don't have to go back and change it, right? But this is 473, okay? So it'd be 4, 7, and 3 zeros. All right. Now we know that with disk capacitors, whatever value this is in picofarad. Okay. Now, again, I would never ask you for a 47,000 picofarad capacitor. Like that's a mouthful. No thanks. And so I would move that back 3 decimal places, 1, 2, 3. And I would say it was 47. And picofarad is times 10 to the negative 12. So I got to go up in my unit. So that would be times 10 to the negative 9, which is nanofarad. So like the perfect Mike Crash answer would be 47 nanofarad. Like that's what I would have written. Again, like we're being a little pedantic here. It's not a huge deal at all, but I just wanted to tell you why, like where I come down on that. This one, 470 microfarad, it's printed on there, and like that's engineering notation. Done. I like that. That's fine. Same thing here, 2, 2, and 4 zeros. 2, 2, 1, 2, 3, 4, right? That's in picofarad because it's the disc capacitor, Mylar capacitor, but same idea. So again, I would move my decimal place 1, 2, 3 times and change that to nano. So that's what I would have put for that one. Now, this one is always an interesting one with kids. It's printed on there, 0.1 microfarad. 0.1 microfarad is what it's printed on there. And basically every kid's going to write that for an answer. But again, if we're being snotty and pedantic about it, that's not engineering notation either, right? When you have that 0 in front of the decimal point, technically that's not engineering notation. So I would move my decimal point 3 spots to the right. 1, 2, 1, 2, 3. And I would go from micro now down to nano. Like that's, again, that's what I would do. So just so you guys know, like that's if I was doing it, that's what I would do. It's not a giant deal, but people were kind of all over the place with if they're leaving things in picofarads, if they were changing them, if what they were doing. So I just wanted to get some clarity on that. Okay. Anybody, any questions on that? Okay. Okay. Cool.
Wait, actually, yeah. I do have one question for that last one. E, it just says 102. What would you do for that then?
Okay. So, wow. So 102. All right, we'll zoom in. So that's 1, 0, and 2 more zeros. 1, 0, and 2 more zeros. So you'd start by writing 1,000. 1, 0, and 2 more zeros. Oops. And because it's a disc capacitor, that's in picofarads. Now, technically, that's not engineering notation because I have 4 numbers here. So I'm going to go back 3 decimal places. 1, 2, 3. And oops, that would be in nanofarad. For better or worse, almost every answer here is in nanofarad. Just sort of, that's just coincidental that's how that worked out. But thanks for asking, Tyler. Okay. Groovy. So on to some big stuff for today. So yesterday I hinted at, well, maybe more than hinted, I talked a bit about the random number generator, not a dice kit. And that's what this morning is going to be focused on primarily, is this random number generator, not a dice kit. So I'm going to pop over to 119. Oh, let me talk about 118 just for 2 seconds. This is the soldering practice fun light kit. I'd skip this one. I can give you lots of cooler soldering projects if you want to do more soldering with your kids. I can give you way more fun things to do. This thing's pretty lame, I think. It's like, I don't know, $8 or something. So it's not terribly expensive, but it's not really all that interesting. So I would do a different kit if you really wanted to. But I don't think you have to. I have kids start their very first soldering they've ever done in their entire life is on this random number generator kit, and it's fine. It's not, I don't usually run into that many issues. So here's a picture of it. It's a pretty poor quality picture. Sorry about that. But here's a picture of it. You get this printed circuit board. Okay. And it's got, everything silk screened on it. And then you get bags of components, and, these are all the components on here. I know I've said it before, but it's worth saying again, pretty much every single part on this kit is something that you guys will stock in your lab for like other DE stuff, right? For your activities and that sort of thing. So if a kid bends the pin on this chip right here, you're like, hey, don't get too bent out of shape. Here's another one I've got in the cabinet. Here you go. Okay. This is a 7474. This is 74 LS08 or whatever. And you should have those in your lab for your other activities. These resistors, these are all 180 ohm resistors. You'll have extras of those. These are LEDs, obviously, which you're going to have more of those. This is our friend, the 555 timer. You're going to have those. The only thing you won't have like extras of probably are this little slide switch here in the bottom left, and maybe this push button over here. And there's a battery holder, a battery snap on the back of this thing. You can kind of see the shadow of it through the board here. So those are the only things you're not going to have like extras of floating around your lab. And the kids don't break those too often. I don't want to say never, because it does happen, but and you could, by the way, you could certainly purchase extras of these, if you want to just go to some different websites I can show you later and pick up extras of those parts, you can. But I think it's pretty neat. By, let's say, by the end of the third quarter of this class, whether on quarters or not, whatever, but by the time you're 75% through this class, you would effectively be able to design this entire thing from scratch. Okay, you'll have the skills and the techniques to design this whole thing from scratch, which I think is pretty freaking neat. So that's pretty cool. Right now, we're gonna let them tell us what to build, because we don't quite have the skills mastered yet. But it's a nice little carrot on a stick. So they've got a video in here, and they tell you what you should have. Oh, this is what the board looks like when it comes from the factory. And they give you really good instructions, nice pictures of how to solder this whole thing. Okay, so you can do that. The biggest teacher tip I have for you. Okay, so kids are going to solder these in upside down. Some kids are. All right. You can see there's a little half circle cut out of these sockets. Okay. That's supposed to match the little half circle on the chip. Okay. They, on this kit, they face down, like the little circle is facing down. And if the kid's looking at if they're looking at the silk screen, look, there's like the little cutout. Little half circle, match the little half circle. And there's like text here about how to solder it in the right direction. And yet I'm going to estimate 40% of your class will put them all in wrong, or some of them in wrong. It's the thing. Okay. And then they're going to ask you an interesting question. They're going to say, does it matter if this is upside down? And the question is sort of like, the answer is like, kind of not really. So these sockets, they only serve one purpose, really. These chips are really heat sensitive. So if you try and solder the chip directly into the board, which I've had students do, you're probably going to destroy the chip, right? Soldering irons are very hot. That heat will travel up the legs of the IC and probably burn out the chip. So these sockets let us solder the socket in, because it's just metal and plastic. Wait till it cools down, then we can put the chip in, no heat damage, right? So they don't have any like electrical function, so all they are is metal going down. So if a kid puts the socket in upside down, it doesn't really matter. It kind of matters though, because the chip still needs to go in the correct direction. The chip does matter which way you put it in, right? And it'll be a little confusing for them if these half circles are on the top when they're supposed to be on the bottom. They got to get the chip. The chip's got to go in the right way. The socket doesn't matter as much. Okay. I'll usually give them a little guilt trip, like, well, in 30 years, when this chip burns out and somebody's got to replace it, they're going to look at the socket to guide which way the chip should go in, and your socket's going to be upside down. And they're like, should I resolder it? I say, no. Don't resolder it. These are a super hassle to take out once they're soldered. Ugh. Really, you'd need to heat all 14 pins at once with your soldering iron, and that's pretty difficult. They actually make specialized tools that are like, I don't know how to describe it. I'm like a squid looking thing with like 14 little soldering iron tips, so you actually can heat all of them at once. I don't have one, but they do make them. So that's a big mistake that kids make. The other one, and again, there's a big point on it here, but of course, reading is hard. There's these 3 holes right next to each other. The battery snap goes in these bottom 2 holes. Okay. That's the one it goes into. You'll notice this little line here. See this little line? That's a copper trace, a metal trace. It's like a wire, right? And if you put your battery snap in here in these 2 holes, which you can do with a little effort, it perfectly fits in here. But if you squeeze it a little bit, you can get it in here. Kids will do it. Then you're taking your power supply, which is 3 batteries here, 4.5 volts, and you're basically short circuiting it. You're making a short circuit because you're just doing a wire from positive to negative. Now, what will happen when you do that? A short circuit has a really low resistance and voltage remains constant. We talked about this with Ohm's law. So if resistance goes down, current goes up. Okay. And batteries have a lot of current capability. And the other thing that comes with current, with lots of current, is heat. Okay. One of the reasons why short circuits are so very dangerous is because a huge increase in current is a huge increase in heat. And so what will happen to you, I can almost guarantee at some point, is you're going to hear somebody be like, this thing's hot, right? They'll freak out because, and they get really, really, really hot, right? I've seen these battery packs melt, right? I mean, they get super, super, super hot because they're creating a short circuit here. Okay. It won't like spark or anything because it's soldered in, but that's something to watch out for. That's probably like the only dangerous thing on here is if they do that. The way I manage this in my classroom is I keep the AA batteries. And when a kid's like, I'm ready to test it, I'm like, bring that over here. Let me see. Let me just take a quick look at this thing, right? I know it's like when Greg's teaching wood shop and he needs kids to, I'm bring that over here. Yeah, it needs a little more sanding. I'm going to give that a feel. Sand that for another 10 minutes. So I can take a look at this thing. And this is one of the things I look at every single time. Did they get this battery pack in the right place? If not, no batteries for you. You made a mistake, right? I'll usually check the chips, things that take me 10 seconds to look at. Are the chips in the right way? Is the battery pack in the right way? Are they missing any components? Anything like that. This little piece of double stick tape is lovely, and it doesn't come with the kit anymore. Somebody over at Vex Robotics made the business decision to no longer include this piece of double-sided tape. I don't know how much that must have cost. They probably high-five themselves for saving 2 cents. But anyway, that doesn't come with it anymore. I like it. You should do it. Anyway. So this is 119. It's a nice little thing. At the end of it, the only artifact they really have is they roll the dice 100 times, which they crab about 100 times, but it takes like 5 minutes. It's fine. And so they roll the dice 100 times, and then they write down how many 1s, 2s, 3s, 4s, 5s, and 6s they got to see if it's a fair die. Spoilers, it won't be. There's something about the design of this, and we've as like master teachers, we've argued at length about why we think it's not fair. So to tell you the truth, we don't have like a really good answer for why it's not fair. The best explanation has to do with the current draw. When one LED is lit up, it doesn't draw nearly as much current as when 7 LEDs are lit up, 6 LEDs are lit up. And so it tends to land on like 6s and 1s more typically. But yeah, it is what it is. It's an interesting kind of a thought experiment for the kids, and you can be like, yeah, so if it were really important that this thing be perfectly fair, like what could we do, or what choices would we have to make, that sort of thing. But there you go. Okay, any questions on 119 on the soldering of it? Okay. For various liability reasons, I'm not going to teach you how to solder remotely. But if you guys ever want to have a conversation about it, outside of the Zoom or whatever, or outside of this session, I should say, I'm happy to talk about it. You should check safety rules for your state, your county, your whatever. I will tell you a couple big misconceptions. The solder that you should use, I think, is tin and lead. It's a mixture of tin and lead. In the United States, that is legal. In other countries, they have the law called RoHS, Reduction of Hazardous Substances, that requires most solder to have no lead in it. And I am an environmentalist. I think that's great from a commercial aspect, but leadless solder is much more difficult to work with. From a human perspective, the robots, they can solder all day with leadless solder. Fine, let them do it. But for you guys in your classrooms, solder with lead in it has a much lower melting point, much easier for kids to work with. Now, lead is a bad thing for you to have in your body. But misconceptions: lead does not vaporize. It doesn't go into the air at the temperatures that we're using. Okay. So if anybody tells you that kids are breathing in lead, no, they're not. That doesn't happen. It does get on their hands. So I would recommend you don't let them like eat or drink or put on makeup or whatever when they're handling lead solder, right? Make a point of being like, all right, go wash your hands, go wash your hands, go wash your hands. If you happen to have a sink in your classroom, that's great. They make de-lead soap, like hand soap for like getting lead off your hands. I think it's mostly for like, firearms, that sort of thing. People handling a lot of lead there. But anyway, they make a soap like that if that's what you're into. But you'll see a lot of stuff about like ventilation, like you should have ventilation. But most of those rules are for people that are soldering for like 8 hours a day, like if it's your job to solder. Whereas your kids are going to be soldering for 30 minutes, 40 minutes, 50 minutes. Michael asked in the chat, how long does this take to do this activity? I would say minimum in my days, my 50-minute days, I would say about a day and a half is like the quickest. Some kids are finishing it in that second day. If a kid messes a bunch of stuff up and has to like desolder and do that, probably on the long end, 3.5 days. And I'll tell you kind of what I do. Some of the kids are working on the computers. Some of the kids are soldering because of how it works. So no one's twiddling their thumbs waiting for the other kids to finish, I guess is what I'm trying to say. Okay. So my disclaimer is that, you should find out what all of your rules are in terms of safety and make sure that you're doing it as safe as you can. But kids absolutely can solder in the class and do it safely and all that. And they love it. So there you go. All right. Net exam just finished telling me that my attendance was taken. So 24 minutes later. Thanks, Net exam. Okay. So anyway, on to the topic at hand. We've kind of got back to an order now. Remember I told you that the first couple of days we were all out of order. We did 115 first and then we were jumping. But I think now we've actually sort of settled in. We've done, I believe, every activity up to this point now. 1-1 was all the introductory stuff. 1-2 got into our, circuit design. We did our seatbelt circuit. That was 1-2-1. We looked at signals together. That was 1-2-2. You did the binary activity, which was 1-2-3. And then yesterday we did 1-2-4 and 1-2-5, where we built that counter, that 4-bit counter, and the 5-5-5 timer to run it. That little wave generator that ran it. Now this has put us perfectly in position to build our random number generator. And by the way, when I say build, I mean design. We're going to design this random number generator. Now, again, they give us the design, but we're starting to sort of understand a little bit at a surface level why they're making the decisions they're making. Okay. Now, the activity, I kind of like the activity the way it is. Although, to be honest with you, I would probably flip 127 and 126. So let me explain more when I get into it. So they start with the wave. I need my counter, count, and I need my wave to tell that counter how fast to count. That square wave tells my counter how fast it's going to count. You guys, yesterday when you were doing your activity, they asked you to like change the frequency, and they're like, change it so you can count. And what frequency did you pick, right? Just to give you kind of a concept of how fast frequencies are. And so we need a frequency that makes this dice roll. So the numbers are like blink, 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 blink. So it looks like it's rolling because that's fun, right? But it is not so slow that I can pick a number specifically, right? And so they have this cool little circuit that we're going to talk about here in a minute. Before we do, a nice little presentation they put in here. I like this presentation, parts of it. Okay, so this is called a block diagram. And block diagramming is really helpful and really useful in a lot of ways, because what we can do is we can be like, I describe what I need. Maybe I don't know how to do it yet, or I don't like fully comprehend how it's going to be done, but I can put a block and say, all right, so in this block, okay, in this block, in this middle block, I need to count from 1 to 6. I don't quite know how to do that yet, but I know that's what needs to happen in this middle block. Right here, I need to count from 1 to 6. And over here, on this block over here, I need to create a wave that will trigger this count. That'll tell it when to count. So this section, I need to create a wave. This section, I need to count from 1 to 6. And you can kind of see, here's my wave coming from this block to this block. And it's weirdly shaped, which I'm going to talk about in a moment. And then in this block, I'm counting to 1 to 6, but it's in binary. And I mentioned yesterday that would be quite the nerdy random number generator. So in this last block, in this right side block, we're going to convert the binary number to a dice display. So I have 3 unique sections here that I'm going to deal with. And so if I'm designing a circuit on my own, I'll do block diagrams to like, okay, I don't need to know how to do the entire circuit yet. Let me just like get some ideas down of what I need to do. That helps structure my thought process. Number 1. Number 2, if you're in a larger company, they might task this block to a different team, right? They might say, all right, so, you know, Caleb and Laura, they're working on this block over here. And Randall and Zach, they're working on this block over here. And then, you know, you guys will just connect them together after the fact. So this is a pretty common thing to see. Okay. Now, cool things that they did. I love this design. It's very clever. And, you know me, I'm not humble. And I wish I could take credit for this, but I didn't design this. I don't think I would have come up with this design. And I'll show you. I think it's so cool. So when you roll a die, okay, it doesn't, when I throw the die down, it kind of rolls, right? You throw it and it kind of, and it lands, right? And what they did was they sort of approximated that with electricity. Let me show you. So this should look a little familiar to you. We've got a 555 timer. We've got what would be called RA, RB, and C. This is just like a regular 555 timer circuit that you built a bunch of times already. But they added these little things over here. They added an extra resistor, this little switch, and this big capacitor. Now, why did they do that? So what they did is they made a regular 555 timer that rolls, that creates a wave at roughly 66 hertz. That's its like rolling speed, but right, 60 times a second, pretty fast. Okay. Okay. But what they did is they added this. Now follow me through this here, and then ask me questions after the fact to see if you check for understanding here. So when this switch is closed, you're pressing the button. Okay, you're holding the button down. The dice should be rolling. So my voltage comes down here. It runs the 555 timer, and this is do 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 do. It's rolling. Okay, rolling, rolling, rolling. Everything's great. But while it's doing that, we have this capacitor over here that's in parallel. So quietly, without really affecting this circuit, this capacitor is filling up. It's filling up, it's filling up, it's filling up, it's filling up. And eventually it gets totally full. And a capacitor that's totally full basically acts like a break in the wire. So when this capacitor is totally full, it's like it doesn't even exist. The circuit doesn't even know it's there. Okay. But it's been charging its battery over there, so to speak. It's a big full tank of voltage. Okay. So then when you let go of the button, you are disconnecting power from this 555 timer. It should stop working immediately, right? So whatever it's rolling, it's 1, 2, 3. Oh, it should stop immediately. But this tank all of a sudden is not being filled anymore. And oh, it's got a path. So that capacitor starts running the 555 timer. It takes over. It's not, tell the kids, it's like it's running on battery backup here. Okay. So all of a sudden this capacitor takes over and it starts running the circuit. So for a moment, you don't even notice, right? The 555 timer's happily still click, 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 click at 66 hertz, right? But that is short-lived because, as we know, capacitors discharge quickly. They empty quickly. So this voltage starts to drop pretty quickly. It starts at 5, but pretty quickly it's 4.2 and 4.1 and 3.8. And the function that starts messing with the voltages at RA and RB and C, which, as you guys know, controls that speed. When you guys changed RA and RB and C, you changed the speed of this roll. So as this capacitor empties, your roll slows down. And eventually, this capacitor empties so much, there's not enough voltage to even run the 555 timer. It stops. And so it gives us that dice roll and stops. That's so cool. It's so clever. What a great design. It does exactly what we want it to do. It has the added benefit of like being even harder to game the system, right? You're like, oh, I need a 3. And you try and let it go, but it still has some roll to it, right? So you can't let it go right at the 3 because it'll and it'll keep rolling, which is really neat. And when you're ready to roll the dice again, you just press the button down. The whole process starts over. The capacitor fills, and when you let go, the capacitor empties. Such a cool design. Love it.
Those other much smaller capacitors that also like before for stability in the flow through there.
So C3 down here, down in the bottom right, C3 is a buffer capacitor that is only for stability. It doesn't affect the timing. C2 is does affect the timing. That's the design one that you guys were doing your math on.
Okay, yeah.
Mm-hmm. So any questions on that? Like I said, it's not expectation that the kids would be able to design this at this stage, or you. I wouldn't have come up with this idea. I think it's super neat and clever, but pretty cool. Okay. So here they show you on the oscilloscope what this should look like, and you guys are actually going to measure this. You're gonna have this circuit built, and you're going to measure this. And we're going to measure the wave early in the beginning here. We should see a very small period, very high frequency. And then you're going to measure it somewhere in the middle over here. And we should see a larger period, smaller frequency. It's slowing down. And you're going to measure the last wave right here before it flatlines. And we should see the slowest frequency. So you're going to measure in 3 different places to demonstrate that it's slowing down. And so that's part of what you're going to do in the activity. And I'll show you. Okay. Here they're showing this little thing down here is C2. See it charging, discharging, charging, discharging, charging, discharging, charging, discharging. It's slowing down with the wave. And then this one over here is your capacitor C1. See it emptying. Empty, 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 flat line. Yeah. Okay. So this thing is our analog section. Remember the block diagram I showed you a moment ago? This is that leftmost box. This is how do we create a wave? And not only a wave, but this cool damped wave that slows down over time. Okay, so I'm gonna go back to the very beginning. That's this box right here. Wave that starts fast and slows down. That's the first thing that the kids are gonna build and test and work on. The neat thing then is that like this is on that board they soldered or are going to solder. They can find the 555 timer. They can find RA, RB, and C. They can find this little buffer capacitor. They can find this big bad capacitor over here. This push button, like this is exactly component for component, value for value, what's going to be on that board, which I think is neat. I think that's cool. Okay, so you are going to, in the It's Your Turn portion, you're going to be building this and sort of experimenting with it a little bit. You have, reminder, you have built this 90% of this before. So go back to those earlier schematics, copy it, paste it, whatever. If you want to build it from scratch, you can, but why, right? You got the 555 timer, you got RARBC, the buffer capacitor. All you have to do is copy that and then add these few little things. Okay. So that's 126. Here's that activity. One thing they recommend, and this is a great recommendation, instead of the push button, that's what this thing is a push button. And that's what it is on the actual board. They say, you know what? Why don't you put this guy in instead? Because that way you don't have to like click your mouse and hold it, right? This little toggle, you can click it once, it closes, click it again, it opens. This is a little bit easier to use. We have not seen that component yet. So if you want to write it down, that's an SPST. It's written right here, SPST, single pulse, single throw. The other change they recommend is instead of using 100 microfarad capacitor over here, they suggest a 50, because if you're like me, you're impatient and you don't want to wait for the whole thing to charge up and then discharge. Remember, you're simulating. Depending on how beefy your computer is, it might take a really long time for it to roll all the way and stop. In real life, it takes about 3 seconds. But again, depending on how slow the computer is, you might be waiting 15 seconds for this thing and you're like, forget it. So if you make this 50 microfarads, it'll happen a little bit quicker. That's the only difference you'll see.
So Mike, when you're designing something in Multisim, and you're talking about the differences between when we're simulating it versus real life.
Yeah.
Now in Multisim, how long Multisim thinks has passed? Is that relatively accurate to what would happen in real life?
Yes, that is relatively accurate. Yeah, it's a great question, Randall. So yeah, if you look at the actual transpired time, that should fairly well represent reality. But we might have to wait 40 seconds to get 3 seconds to pass in Multisim time. So especially, by the way, especially when you have the oscilloscope on. The oscilloscope, without diving too deep on this, the oscilloscope is a lot of data that Multisim is gathering and analyzing. There's a lot of deep math going on in the oscilloscope. And so as soon as you add an oscilloscope, you'll notice that your computer goes, whoa, man. And all of a sudden that transpiration time, that slows way down, because this is tough for the computer to deal with. All right, here we see that idea again of the damped wave. And here's where it's asking you to do that measurement. Measure the wave in the beginning, measure the wave in the middle, measure the wave at the end. One big misconception that always happens right here. So let me clear this up right now if I can. When it says first square wave, that doesn't mean like when you turned Multisim on. Okay. It means as soon as you let go of the button, right? I held the button, it's rolling, it's rolling, it's rolling, it's rolling, it's rolling, it's rolling, it's rolling. I let go of the button. Right then, that's when you measure the first wave. Okay. If you measure like as soon as you turn on Multisim, you're going to get weird results. So as soon as you let go of that button, that's your first wave. And if you need help with that, you know who to ask. I'm here. I'm happy to help. Okay. So 127. So 127 is the other half of this circuit. So we created the wave. Now what? So there's another little good presentation here about it. This is the part I was saying I would flip. I don't like. So we got to deal with these two sections, the middle one and the right one. And they start with the counter first. I think I would do this first. I'll explain why in a second. So this is our count to 6. Okay, count from 1 to 6. Now, things that you may recognize. What are these rectangle-y things? Anybody remember what those are called?
Flip-flops.
Flip-flops, that's right. These are our D flip-flops. Flip-flop, 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 which again, we haven't dived deep into yet, but we will. But we've seen them. We've built them a couple of times, and we've kind of wired them up this way before too. When we built our 4-bit counter, this is roughly what we did. The difference in that time is that we had 4 flip-flops. This time we only have 3 flip-flops. That means as high as we could count with this little guy right here would be 1, 1, 1 in binary. Grab my pen here. 1, 1, 1 is the high as we could count, which if we bring up our little chart here, 1, 2, 4. So 1, 1, 1 would be 4 plus 2 plus 1, or 7. 7's as high as we could count with 3 flip-flops. But that works for us, because guess what? We don't have to count beyond 7, because this thing is designed to go from 1 to 6. So we don't need any more flip-flops. Perfect. Okay. Now, for right now, and again, please, please, please trust me. For right now, I'm just going to tell you this section right here is what keeps the count 1 to 6 instead of 0 to 7. I absolutely promise we are going to do a lot of work on why that does what it does and how you design it and blah, 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 blah. That's like all of Unit 3 is this thing over here. Okay. So I promise we're going to dive in, but for right now, take Crash's word for it. That chunk of stuff over there makes our count 1 to 6. That's what it does. Okay. All right. Boop. There we go. Now, for whatever bizarre reason, they take us through everything. And I don't think these is particularly easy to read. They're telling us that this is a 1, 0, 0, and then like, okay, now these are green and these are like, I don't take a lot out of this personally. And it's okay at this point to be like, this is a thing that counts. You guys built your 4-bit counter. You saw it do its thing. It's like that. The kids are like, okay. You're like, all right, cool. We're not going into what's happening at each stage yet. Look at that amazing animation. So we did this counter. Now, out of this counter, we have a binary number. We have 3 wires that are giving us some binary count. 101. Great. The heck does that mean? So this last section, this combinational logic section, is going to, sorry, this is overlap. Let me leave it here. It's going to take these 3 wires that have a binary number on it. So for example, let's say this is 1 and this is 0 and this is 1 coming in. Now, that would be 5 in decimal. So the job of this section right here is to say, all right, when I have 101 coming in, what LEDs do I need to light up? What does a 5 look like on a die? Well, it would be the corners, right? And the middle one. So those are the ones that should be on. And also, this one should be off, and this one should be off. Can't always talk about what has to be on. You got to talk about what has to be off too. So this rectangle has to deal with that. If I put 101 in, which LEDs are supposed to light up? That's what the circuit in this rectangle is going to do. And it's got to deal with the other combinations too. If I put a 1 in, what happens? If I put a 2 in, what happens? Right? That's what we got to deal with in this rectangle. So let's see how they do it. Okay. So again, we're not designing this. They just sort of did it for us. But some things that they did to make this circuit more efficient, right? They made it cheaper. They made it take less chips. They made it less power, take less power. They made some decisions here, some engineering decisions to make this thing work better. One of the things they noticed, which I thought was kind of cool, is that L1 and L5 are always on together. And I know I had to take a die out and be like, wait, what? Let me, hold on. All right. So when I have a 2, they're on together. Sorry, let me start over. When I have a 1, they're both off. 2, they're both on. 3, they're both off. 4, they're both on. 5, they're both on. And 6, they're both on. Heck, they're right. Every time L1 is on, L5 is on. So intelligence, efficiency, don't build 2 circuits with double the gates and double the hassle and double the wiring. Just run both LEDs off that same circuit. Brilliant. Not only that, the same situation happens with L2 and L6. They're always on at the same time. They're always off at the same time. And L3 and L7, always on at the same time, always off at the same time. So that saves us a ton. Woof, man, that saves us a ton of circuitry and wiring and designing, the fact that those things come on and off at the same time. Okay. L4, the cheese stands alone. L4 is by itself. That one doesn't, that is not paired with anything. Okay. And so they designed these gates here. Now, this is not quite so simple as like the seatbelt circuit where we could like talk it through and be like seatbelt not buckled and door or key in the ignition, blah, blah, blah. They've done some simplification here, which is something that we're going to learn about this afternoon, actually. No, that's a lie. Tomorrow, we're going to learn about that. But basically what they have found is this little circuit does what we ask. If I put in 101, which we talked about before, it's going to light up L1 and L5 and L3 and L7 and L4. It's going to light up those LEDs. And it's not going to light up L2 and L6. Now it does take us, I think it takes us through that a little bit here, if I'm not mistaken. So that's worth looking at for a second. And let me show you 5, because that's what we were just talking about. Yeah, there we go. All right. So when I put in that 5, 101, let's just take a quick look. So I have a 1 and they do green for 0. I have a 1 and a 0 going into this OR gate. And the OR gate gives me a 1 if either of the two legs is a 1. And since this is a 1, boom, the output's a 1. Okay. Here I've got an AND gate. I've got a 0 and a 1 going into my AND gate. Oh, well, that's no good because on an AND gate, both of the legs have to be a 1 in order to get a 1 output. So my output here is a 0 as a result. But it turned out it didn't matter because this one was a 1. Didn't really matter if this one was a 1. These guys light up. Down here, I've got one of my legs is a 0. One of my legs is a 1. Oh, but this is an AND gate. So the output is a 0. So L2 and L6 don't light up. Well, that's what I want. That's good. And down here, my OR gate's got a 1 on it. So it lights up L7 and L3. Again, we will learn how to design this. Right now, we're just appreciating like, oh, neat. That's what kind of what it does. It does a thing. They're going to make a big point in the activity about this. This is a truth table. You saw them already when you did 116, when you were playing with gates and you were turning them on and off and you were writing down what happened. You saw a truth table. This is a much bigger one, a little bit more intimidating, this one. Okay. But it does the same thing. We look at combinations 0, 0, 1, which is a decimal 1. And we'd say, what should be lit up when we roll a 1? What should be lit up? Turns out just that center LED, right? A 1 on a die is just that center LED. And so that one is a 1. The rest of them are all 0. That's what goes in this truth table. And then here this is a 2. This is a 1. This is a 2. So for a 2, the corners light up. 2 of the corners light up. So L3 and L7 light up, and everything is 0, else is 0. So this is how we kind of prescribe what we want to happen as we go through our circuit. Now, on the activity, they're going to have you put in a 0 and see what happens. And they're going to have you put in a 7 and see what happens. And you're going to get weird results. I think, if I'm not mistaken, I think you get like a 2. Like I think you get like 1, 1 here on the 0. And the 7 actually might be all of them lit up. I don't remember. But the point is, you run into a really interesting, what's the word I'm looking for here? Philosophical thing, design thing here. Do I care what the LEDs do if I give it a 0? Do I care what the LEDs do if I give it a 0? The answer is no. Because does my die ever roll a 0? No. You know why? Because we designed that last step, we designed it so it only goes from 1 to 6. It never, ever, ever goes to 0. So I don't need to tell it, turn off all the LEDs when it's at 0. I could. You could. You'll have the skills to design it. You could make it do that, but you don't need to, and it would be extra gates, extra complexity. And so we call this a don't care condition because we don't care what happens there. You could light them all up for all I care. You could light up half of them. You could light up, doesn't matter. Same thing down here with the 7. We don't care. In normal operating procedure, our die will never, ever, ever show a 7. So we don't care what happens on the 7. They make a big deal about that in the activity. They're like, what happens when you get a 0? What happens when you get a 7? Why is that important? It's because we don't care. We don't care what happens at 0. We don't care what happens at 7. And that's a really important concept when we get later in our curriculum and we're designing the most efficient circuits. And boy, it becomes really real for you and for your kids because they're like, if I spend 5 more minutes in the design process, I can save myself 2 hours of breadboarding because I eliminated 4 chips and all these extra wires and everything. Like, it becomes very real. Not to mention from a commercial aspect that every chip you save is money. Every chip you save is less battery drain. It's less heat that we have to deal with. It's less chips the factory has to stock. It's less solder points. Like it really cascades how important it is that we eliminate as much complexity as possible. So questions on the sequential, which is the county part, or the combinational, which takes that count and turns it into the dice roll. Questions on that? Okay. I don't know. I don't think there's anything else in this PowerPoint that we need to talk about, but I'll just double check. Oop. And again, I don't go through these slides with my kids. Like, they're not getting much out of it. Oh, they do remind you that these are probes, which are a multi-sim only thing. They're magical fantasy land. Those little lollipops, you know, there's not like a real world thing. They remind you that when we're in the real world, those will be LEDs, and LEDs require a current limiting resistor. So that's just what they throw in here at the end. They're like, hey, by the way, don't forget, you're going to actually have LEDs with resistors when this thing hits the real world. Okay. All right. So we got a big chunky piece of circuit here. We've got our sequential logic. This is a 3-bit counter. Where's my pen? Boop. This is my 3-bit counter. This is my section that says, yeah, but you're only going to go 1 to 6, buddy. And this is my section that converts that binary number into LEDs lighting up in a die formation. Here are the LEDs. And then I think they got lazy. The 555 timer, cool damped wave thing that goes here in this box. So I campaigned for years. This activity never had kids put the whole circuit together in one multi-sim. And I was like, why not? That's the coolest part. And they finally changed it. So now at the end of 127, the kids put everything beginning to end, 555 timer, sequential logic, combinational logic, LEDs, all are in the same multi-sim, and they can hit the button, make it, and then roll, and they can see the whole circuit, which I think is pretty cool. Okay. All right. I have to say, okay, I'm going to write down, I have to say one more thing, but it's break time. So I will talk about it right after break. Okay. Let's take a quick break. We'll come back.
Mike, real quick.
Yeah, Eugene.
For the deliverable for our work, it says 127. Add screenshots of your responses.
Yeah, I'm actually gonna talk about that right after break. That's the thing I need to talk about after break.
All right.
That's okay. And if I don't answer your question, then ask me again.
All right.
Okay. So let's take a quick break, 5 minutes, and then we'll come back and talk about that. Resume. Okay. So when you go to make this lovely circuit, this random number generator circuit, as you can see, it's a little bit of a beast of a circuit. And your kids will do this whole thing. I do recommend to them, hey, like go back and you've built portions of this before. You built some 555 timers. You built some, some counters, feel free to copy that if you want and save yourself some time. This is also a great time as a teacher check to see how your kids are labeling their files that they're creating, what their kind of naming scheme is for their multi-sim files. You will find kids, there might be people even in this Zoom room right now that have 15 files called design 1 and design 1.1 and design 1.1.1 and design 1.1.1.1. So it's a good spot now to be like, hey, let's talk about how we can name these files so it's a little bit easier to find. And that's going to get more and more important as we go on, right? So if I say, hey, Zach, that, why don't you take a look at activity 216 that you did in Multisim, because you can use that structure. Then if Zach has to go through 85 million files to find out where 216 was, like that's a hassle. The beauty part is, of course, that that your DE curriculum numerically is numbered already and it's labeled pretty well. And so there's nothing wrong with being like, hey, this activity we're working on right now, 126, right? I'm going to save as 126, or maybe even 126A, 126B, 126C if I'm doing revisions within an activity. And so it's a good moment. If you do, my opinion, if you make a whole big speech about this and a whole big spiel, like the second day of class, it'll go right over their heads because they don't like, it doesn't refer to anything yet, right? It's not valuable. It's not important to them. But now is about the right time where it again might have bitten them a little bit already. And you can be like, hey, here's a thought, right? What if we are a little more intentional with how we save those files and that sort of thing? So
I wanted to just throw out there that the way my brain works and my experience with managing files and stuff, I started out doing the numerical naming, and after I got a couple files in, I went back and I would put 1.2.6 flip-flop.
Mm-hmm.
So that if I want a flip-flop, I don't have to remember the exactly the number.
That's a great idea, Randall. I've been teaching this curriculum for a long time, and so I know what the heck 116 is, but your students won't, and you may not. And that's a great point. That's a really great point. In fact, I don't know if you guys have seen the YouTube videos. I have to force myself to be like, oh, okay, 117 is data sheets. I should write data sheets next to it. Because sometimes I forget. Great point. Thanks for adding that, Randall. Okay. So that was my first thing. Now, when you guys go to build this circuit, and this is a good teacher thing for you. Okay. Maybe you roll into class, you want to demonstrate something on 126 or 127, and you're like, oh crap, I don't have it built. I don't know where my files are for my summer training. Oh no, how am I going to do this? Well, the good news is that we got you covered. So if you go into, now this is, I think, the first time really that we're doing this as a training, we're going to go to the teacher guide. I'm going to the teacher guide. And if you can, follow along with this. So we're going to go to the teacher guide course. Now remember, if you're in the student course or whatever, you can just go My Library and you can get back to all of your stuff. And so we're going to go in the teacher guide, Digital Electronics teacher guide. Okay. And on the left side, we're going to scroll all the way down to the bottom, literally till it bottoms out. We want the very last item in this menu, and it's called Course Resources. Okay. And there's a bunch of good, important stuff in here, but the very top one is what I'm talking about right now. Multisim CDS files. So that is a bunch of Multisim files for each of our activities. Okay. So if I click that, I'm going to download a zip file. And if I open up said zip file, you're going to see in roughly numerical order various activities where they've built some of the stuff for us, right? So we can open that up and we can grab it and we can use it. So for example, here's 126 and 127 that we're working on right this second, right? So if I open up 126, for example, chugga, 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 chugga. Here we have some of that 555 timer stuff already built. Okay. So this is great to grab and to use. I'm persnickety and I have, issues with some of the ways they build things. And so I just use my own stuff because, I'm a crotchety old man, but this is a wonderful thing for a lot of people to use, as a little bit of a, help you out here. So you don't have to necessarily reference the file or build it or whatever the case may be. Right. So these are really nice to have. Okay. Now in the activity in 126, 127, or in the it's your turn. I believe they recommend that you grab these files that are already built and put them together and use them. So you don't have to build the whole thing in Multisim on your own. Okay. So just a quick conversation about this. You are all professionals. And just so there's a clear expectation, there's times where I want you to build something, and there's times where I'm gonna say, just use the key. It doesn't, there's no, at this point, I don't need you practicing Multisim, right? But like when there's times where I want you to make the design, I'm gonna be like, you make the design, don't grab the key, you make the design. But this is one of those grab the key times. Feel free to grab the key, the circuit, and put it together and test it, right? So there's 1, 2, 6, and then 1, 2, 7. If I open it up, here is the circuit. They have it in a couple different formats here. Here they have just the combinational section on its own, so you can play with that. You can say, all right, well, if I put 0, 0, 1 in, oh, look, the center LED lights up. If I put, here's 2, oh, look, the corner's lit up. Here's a 3, oh, look, the other thing. So you can like play with the individual LEDs. This is just the counter section. So if I clock it, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So that's just that section. And then down here, we have that exact same thing, but fed by a clock. Look at it go. Wee. And then over here, they put the whole thing together. So here I have the analog section, the 555 timer, and it's feeding my counter, count. And my counter is feeding my LEDs, which are changing over here. So you can see all that kind of action going on there. Okay. While I'm here in the teacher guide, you're going to see this word CMOD S6 in various places. That is a chip that we used to use, but you shouldn't use it anymore. So if you have them in your classroom or whatever, you shouldn't use them, and you definitely shouldn't use the activities, etc., that are made for the S6, because that's a deprecated chip that we shouldn't be using anymore. So if you ever see S6, you're probably in the wrong spot. So that's why I downloaded this top one, not the bottom one. I wanted this one, not the S6. Okay, now we use the S7. S7 is good. S7 is where we are. S6 bad. Oh, so while we're here, what I was going to say, while we're here, there's a course presentations. There's a whole zip file with all the PowerPoints, if that's something you're into. And there's some nice assessment resources and things like that. The other thing I wanted to show you, which I didn't show you the other day when we were in here, when you're in the unit, so I'm in like lesson 1, 2, and I can show you where to find this later because I think it's confusing. But under teacher resources, there are like downloadables. There's the worksheets, but there's also day-by-day plans. So for those of us who are, teaching this class for the first time, should be everybody, or, those of us who are newer to teaching, this is a really nice thing. It's not perfect, of course. Everything, what's that expression that, no battle plan survives contact with the enemy? Well, that's probably true for day-by-day plans, right? No day-by-day plan ever survives contact with a classroom. But, this is nice because it gives you a rough idea of how long things are going to take, right? Like, how long should it take to do 1, 2, 2? It looks like it'll take about a day, right? Day 4, you could do 1, 2, 2. And day 5, you should be able to do 1, 2, 3. And day 6 through 8, you should be able to do 1. So like it gives you a rough estimate of how long things take to get through. So that's a nice thing, this little day-by-day plan. They have it for all the units. So you can get a kind of a clue of how long things are going to take. Okay. All right. So that ends unit 1. Boop, done. Random number generator is the end of unit 1. Time-wise, just so you guys know, schedule-wise, I like to finish unit 1 in about 7-ish weeks. From the beginning of the year till about 7 weeks. I like to take a little bit less than a quarter, if that makes sense. We're on semesters now. We don't have quarters anymore, but we used to. And I'd like to get it done in a little bit less than a quarter. Unit 2 and unit 3 are big. So they kind of squeeze outside of a quarter. I like to have maybe 9 or 10 weeks to do unit 2. So I like to get unit 1 in about 7 weeks if I can, just to give you an idea. And again, that's 50-minute periods, 5 periods a day. Now we're on to unit 2. Unit 2, so cool. Unit 2 is where the rubber meets the road, where we're going to really start to design things. Up till now, we've just been like building what they tell us to build. Okay, fine, here, thanks. But unit 2 is when we actually get to design things of our own, which is really neat. 7 weeks in a year-long class, Cindy. Thanks for clarifying. Yeah, year-long class. However long your class is, unit 1 should be less than a quarter of it, less than 25% in time-wise, I think. So I'm going to dangle this carrot again for unit 2. Here's me dangling the carrot. The next big project we're going to do is majority vote. Majority vote. And it's our first circuit that we're going to design and we're going to simulate and we're going to physically build it. We're going beginning to end on this thing. And your design that you create is going to come all the way into chips on board. Okay, in our case, chips in Tinkercad, but in your classroom, chips on board. Okay, that's where we're going to go. So this is pretty cool. All right. What I'm going to need is I'm going to need you to break out your engineer's notebook. Okay, because this is our first big project where we're going to have an engineer's notebook entry. Okay. Again, you don't have to use this one that PLTW provided, but you can if you want. I'm guessing that most of your kids will have already taken some other Project Lead the Way course, IED or EE or POE or something like that. Maybe not, but I'm guessing they have. And so you might want to chat with that teacher to see like how they do engineers notebooks. I would think it would be good if kids had consistency throughout their high school engineering career. It would be kind of a bummer if every year they get a new teacher and they're like, I do engineers notebooks totally differently. So some consistency would probably be nice. So you may want to chat with that teacher. How do you do it? What's your format look like? Do you have examples of kids engineers notebooks so I can kind of see, what was done? What I'm going to lead you through today is how I do engineers notebooks. If you want to do it differently, fine. That doesn't bother me at all. I'm not going to take off points or tell you need to revise it because you didn't do it my way. Okay. I'm just going to do it a way and show you. You're going to follow along in whatever way you want. And then that's what you're going to turn in. Okay. So engineer's notebook open. Let me switch over to share my iPad here. And this is, by the way, exactly what I do in class. This is 216. And you're like, Crash, 216. We just got into unit 2. What the heck? But this is the carrot. I'm dangling the carrot. I'm saying this is the thing we're going to do. We're going to start doing our engineer's notebook entry for it right now. Okay. So for those of us newer to Project Lead the Way, Engineer's Notebooks, Engineer's Notebook can be a legal document, legally binding document. There are some rules and stuff that we roughly abide by. And if you want more info on that, I can direct you to, there's like a nice separate page on the curriculum about the engineer's notebook. So it tells you some details. I am on page 71 because I'm being lazy and using the same notebook I did for my last training I taught 2 months ago. But you're probably on your page 1 or 2 or something like that. So up top, we're going to put our title. This project is titled Majority Vote. Majority vote. Majority vote. You can put 216 on there if you want. It's up to you. I just put majority vote. If you aren't using a fancy Project Lead the Way notebook, obviously you'd want to, write out the word title and put majority vote and all that, but they have a nice little spot for us. Cute. So after the title, the next thing I put is the client. As teachers, you can get creative and fun with these things. In the activity, they go on about like the 2000 election, with like, oh, there was a recount and there was hanging chads and blah, blah, blah. Which, by the way, these kids weren't alive for, which makes me really upset. But that's actually not what this circuit's about. So it starts talking about the presidential election, but that's actually not what the circuit's about. So I think that takes kids in the wrong direction. This circuit is about a board of directors. Okay. Got 4 members of a board of directors, and they're doing like a secret ballot, a secret voting system. So they vote yay or nay for things. We need to know if the vote passes. So it actually doesn't have anything to do with like voting for a president or anything. So our client, I'm just going to put generically board of directors. I've seen teachers do like, senior class executive board or model UN executive committee, or, maybe there's a local company that's really big in your area, maybe like Boeing board of directors or something, make it a little fun and interesting. Next up is the designer, which is you. Write your name, not mine. This is one of the first times we're doing this. This is the time to walk around your class, be like, are you writing it down? Gabrielle, you writing it down? Randall, you writing it down? You got this? You got your book out? You writing it down, right? And model that like the expectation is that you're going to sit here and fill this out with me. You're not going to take a picture of the whiteboard after I'm done writing this down. That's not how we're going to play this game, right? You are going to write it down in your engineer's notebook. That's what's going on. So we got our client, we got our designer. Now, some folks do a problem statement and a design statement as separate things. I just put them into one. That's just like a me thing. So I'm just going to do that. I'm going to do a design statement. So a design statement is a concise, typically 1-sentence statement that describes what the heck it is we're trying to do here. Okay. When you do a problem separate from a design statement, a problem statement defines just the problem, and the design statement designs how you're going to solve that problem, says how you're going to solve that problem. But for these, I usually just put it into one. Okay. So let me describe to you what this is going to be, and then we're going to work on a design statement together as a group. So we have 4 members of this board: the president, the vice president, the secretary, and the treasurer. President, vice president, secretary, treasurer. Okay. And they're going to vote yes or no, yay or nay, on various measures. Should we do this? Should we do that? Vote yay or nay. Okay. And we want this to be like a secret ballot. So that's why we're building this machine. Okay. So they can flip a switch, yay or nay, for whatever vote. And the output will tell us whether the vote passed or whether the vote failed. Light lights up, the vote passed. Light doesn't light up, the vote failed. Okay, cool. And how do we know what passes and fails? It's right in the title, the majority. Okay, whichever way the majority votes, that's the way that the thing works. Okay. So if the majority of people vote yes, the vote passes. The majority of people vote no, the vote fails. Does anybody see any problems with this? The majority.
Abstaining or
That's a great question, Corey. You cannot abstain from these votes, apparently. That would give us an extra state and make it more complicated. So you can't abstain. You have to vote either yes or no. What other issue is there with the majority?
There's 4 people in this group. Is it?
people.
Yeah, there's 4 people. So we have a possibility that there's a tie. Okay, so we have to consider the tie. So here's what happens if there's a tie. If there's a tie, whichever way the president voted, that's the way the vote goes. Okay, so if there's a tie and the president has voted yes, the vote passes. If there's a tie and the president has voted no, the vote fails. Okay, the president doesn't, let's clarify, the president doesn't get to vote again. The president's vote doesn't count twice. It's just the president, it's not always what the president says, it's not a dictatorship. Okay. But when there is a tie, whichever way the president voted, that's which way the vote goes. Okay. So now we need to come up with a design statement. Now I'm going to start it off for us because I like to, basically every single one of these, I start the same way. I say, I'm going to design, build, and test. Maybe I'll write a circuit because this is DE. That now I'm coming to you. All right. So what is the design? I need some language here. You don't want the design statement to ramble on like I did when I described the project to you, right? I talked for 5 minutes about, I don't want that. There should be one sentence that kind of encapsulates the spirit of this design, right? The elevator pitch. What's a quick way of saying what I'm trying to build here? What do you think? A circuit that does what?
A circuit that determines the decision of the board's vote.
Okay.
I don't
I
know.
like some of that language. Determines the decision of the board's vote. Okay. I like that. I like that. It's a little vague. I want like just a little bit more specifics, but I really like where we're at there. Determines the decision of a board's vote.
Interprets.
Interprets. Okay. Interprets a board's vote. Other thoughts? I'm not saying Gabriel's wrong. I want to elicit some more feedback from other folks.
What about that determines the majority decision of the board of directors vote?
Okay. Determines majority decision. Brings in that majority word that's kind of cool because it kind of leads us into that. Determines majority decision. Let's start with that. And then we could maybe let's talk about it determines a majority decision and then does what? What does it do with that? How do we know what it determined?
Well, it returns the answer.
Okay. So it returns the answer. It determines majority decision and returns an answer and outputs an answer and displays an answer, something like that, right? Like we do something with it after we figured it out. Okay, great. And I do this every time. This design statement has been different every single time I've done this project with a group. And that's okay. Like let's talk it through. Let's develop this idea. Now, we should all have roughly the same design statement because we're trying to make the same thing, right? Especially if we do group work, like we want people to have different design statements if they're trying to work together. But this is a good spot to be in. Now, the next thing is constraints. Now, if you teach IED, they have two things here. They have constraints and criteria, which are pretty related. If I'm not mistaken, criteria are sort of like what we want, and constraints are like have tos, right? But I just kind of group them into one group. Constraints are sort of the meat and potatoes of what the circuit's going to be about. And then I usually do it in like bullet point form. I'm not worried about necessarily complete sentences here. The first constraint I always write for every class I teach, every engineering class, the first constraint is always the same. And I'll just write it down here for you so you have it. Must not get Mr. K disciplined. That's a nice catch-all right there. When they're like, can I use a flamethrower? No. Well, I'm going to answer this phone call real quick. So mental break. Hold on. Hello. Yes, Z. Hi. Oh, yeah. Yes. Yeah. Did you call Kristen? Okay. Because she's there with him now, and she could give you a better answer than me. I mean, he's been doing fine. It's just it's been a logistical issue. So yeah, like, well, it was like we couldn't let me mute this real quick. Hi, everybody. Sorry about that. My son is being transferred between two different hospitals. And there's a whole logistical nightmare of insurance and whatnot of him moving back and forth. So he's fine. He's doing well, but it is a paperwork nightmare. So in fact, Friday, when I teach this class on Friday, I'll be coming to you from a hospital room because of that. So anywho, back to the topic at hand. Constraints must not get Mr. Crash disciplined. That's the first one on every list always. Okay, so then these constraints, I'm going to give you a bunch first, and then I'm going to open it up for us to talk about it. So first, we must use 74 series AOI logic. We may not be totally familiar with what that means yet, but 74 series, all of our chips start with 74. And this is and, or, an inverter, which are the only gates we know about yet. We have to use 74 series because that's all I have in my classroom. So that's why it's a constraint. And that's all you're going to have in your classroom, probably. It must be simplified in SOP form. And you have no idea what that is yet. Must be simplified in SOP form. How many inputs does our circuit have? We got president, that's a vote.
Or
Vice president, secretary, treasurer. We have 4 inputs. So we're going to write, we have 4 inputs. And I'm just going to write that they're going to be switches. Not sensors, right? It's not anything like that. It's switches. Okay. How many outputs do we have?
2.
What are my 2 outputs?
This is the 2 votes, either yes or no.
Okay, so yes or no. We have 2 possibilities, but we're to make our circuit cheaper and more efficient. We're just going to have the light lights up. It's a yes. The light doesn't light up. It's a no. So we would call that just 1 output. Could we make a circuit that has 2 outputs? Sure, but we're going to make it a little bit simpler, and we're just going to say 1 output, and that's going to be an LED. Okay, I'm going to pause there for a sec. So the purpose of these constraints, the purpose of a design brief in general, but especially the purpose of these constraints, is to make sure that me as a client and you as the engineers have a very good communication here so that you understand exactly what I want, right? I'm the client. You are understanding exactly what I want. That's what this is. This is not a, not exactly a cover your butt. Oh, well, you didn't say that in the constraints, me, right? Like, okay, maybe you'll get out of that contract, but you'll never be hired by them again, right? The idea is that this list, this design brief, puts the client and the designers on the exact same page or as close as possible. And so when I deliver to you, or when you deliver to me, sorry, when you deliver to me your thing, I'm like, yes, this is exactly what I wanted, right? That's what I'm going for. Now, in the real world, I got engineers in here, you know, that, you know, your client's going to change their mind and they're going to describe something that is not what they wanted and whatever. But the idea is to get as close as possible. So I tell the kids that, like, okay, do you have ideas right now, questions that we can clarify together that need to be in these constraints? Do you see anything missing from this constraint list?
information on the tie.
Eugene, say that again.
Information on the tie.
On the tie, sure. Yeah. I mean, we said determines majority decision, but we didn't really like lay out anywhere what that means. So, so we might say majority wins. And then in case of tie, I don't know, like the non-clumsy way to write this, but in case of tie, president's vote determines outcome. Something like that. Anything else in the constraints you guys see? Okay. And I always end this by saying, if you guys think of anything, we can come back and add it, right? This is not like a final, after this moment, nothing can ever be added to the constraints again, but we can come back to it. In fact, I'll even leave a space right there so I can add things in. The deliverables is the last kind of thing we're going to write on here. So the deliverables as an engineer, what you're going to deliver to your client, it might be a design, it might be a prototype, it might be a manufacturing schedule, whatever it's going to be. In our case, the deliverables are what you give to the teach for your grade, right? So this is a nice little checklist of what needs to be given to your teacher for you to get your grade. And you guys as participants in this training, what you need to put in, I believe it's block 7's turn in or something, you're going to put in this document and all these deliverables. First deliverable, always the same. This design brief document that we're creating right now, that's the first deliverable. I have a huge pet peeve when kids give me their documentation and it's not chronological, meaning this design brief is like 4 or 5 pages in. I'm like, how is that possible? This is the first thing we did. You didn't even know about this project before we did this document. So how is it possible the design brief is 4 pages in? So this is the very first thing in the documentation. Okay. Next up is my truth table. Truth table. Followed by an unsimplified logic expression. I'm going to write this next one in a different color because your students will do this next one, but you in this training will not. Okay. And that's an unsimplified circuit. I'm big on authenticity. I don't like making kids do things just for like the sake of doing them. And so after this moment, I would never ask a kid to do a less efficient version for any particular reason, except for this one time. This one time I want them to do it so we can compare and they can be like, oh, simplification is really valuable. I will do it from now on. Thanks. So this is the only time I'm going to make them do something that's inherently less efficient, this unsimplified circuit. But you guys in this training, I don't want you to do that. Don't have the time. Next up will be a Boolean simplification. With theorems. and then simplified logic expression. Simplified multisim. Two more. Evidence of prototype. And finally, reflection. Evidence of prototype is a nice way to describe, like, are we going to breadboard this? Are we going to Tinkercad it? Whatever. Do you want a picture? Do you want a video? Evidence of prototype is a nice generic way to say that, because depending on what it is we're building, a picture might suffice, but it might have to be a video. When later on you're going to make a 60-second timer, I don't want 60 pictures of each individual state. No, thank you. So you might decide that a video is the best way to show this, or a series of pictures or whatever. Okay. The reflection, just worth saying now, I'll repeat it again later. The kids do this reflection like, this is what I learned on this project or whatever, was what I would do differently in the future, blah, blah, blah. And you're more than welcome to write that as your reflection from the student perspective. But I also, if you'd prefer, to write this from a teacher perspective. Here's what I'm thinking about when I give this assignment. Here's what maybe what I would do differently, or what I'm worried about, or how I'm going to facilitate it in class. If you think that'll be more valuable, do that. That's totally fine. Questions about this design brief? Okay. I have one more thing I need to cover here, and I'm pretty sure it's going to take me a little bit longer than 10 minutes. So I'm going to go. I'm going to do it. If you have to jump out right at the top of the hour, I will not be offended, and I'm going to keep the recording rolling. So if you have to watch it a little bit later, so be it. I'm sorry about that. I got that weird phone call. It sent me behind it a minute or two, but we should be able to do it. And I think like 5 extra minutes, we should be good. So other than the design brief, I would reckon that most of you don't have any idea how to do pretty much anything on this list. And that's great. That's where your kids are, right? They don't know how to do any of these things. But this was the carrot is for. Okay, well, we got to do this cool thing. We got to make the circuit. So we got to build these skills now. Now, what's really nice is this is going to work really well in parallel. 2-1-1 is going to teach us how to do a truth table and an unsimplified logic expression. So you're going to do 2-1-1, and then you'll be able to do the first 2 parts of this project. And then we're going to learn how to do Boolean simplification, and then you'll be able to do it on this project. And then we're going to learn how to turn it into a circuit, and you're going to do that on this project. So like it scaffolds really nicely, and we get to do this project while we learn how to do it. So that brings me to 2-1-1. Okay. I'm going to do it on the paper here to keep my steam rolling here. So 2-1-1 is truth tables. Okay. Truth tables. So a truth table, you guys have seen a bunch of them already. Remember that the purpose of a truth table is to just describe every possibility. Okay. So a 2-input truth table, let's do like A and B, and then my output would be Z. Every possibility has to be in here. That would be 0, 0, 0, 1, 1, 0, 1, 1. That's it. That's every possibility of those 2 inputs. Now, I did that in binary counting order. If you look real quick, it'd be 0, 1, 2, 3. This is not negotiable. When we make truth tables, we're always going to make them in binary order in this class. Would they work if you don't? Sure. But I am telling you, as a teacher, as a human, do it this way. It is going to be such a giant hassle for you if you don't force kids into this. Genuinely. When I first 2 years I taught this, I'm like, I'm laid back, I'm hip, kids can do what they want, it's fine. No, don't do it. Force them into this, and your life will be made so much easier, and theirs, really. What you're going to have is you're going to kids be like, I know, I'll start with like 1, 1, and then 0, 0, and then blah, 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 blah. And they're going to miss combinations. They're going to double combinations. No, don't do it. The cool thing is, though, you're like, but my binary is not so strong, Crash. That's okay. Don't panic. I'm going to show you a trick. So if I want to make a 3-input truth table, A, B, C, here's the little trick. Watch this. In C, in this first column, the far right column, I'm going to alternate every one. I'm going to go 0, 1, 0, 1, 0, 1, 0, 1. In the next column over, I'm going to alternate every 2. 0, 0, 1, 1. 0, 0, 1, 1. And in the next column over, I'm going to alternate every 4. 0, 0, 0, 0, 1, 1, 1, 1. Doing what I just did actually put it in perfect binary order. That's a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7. So I don't have to remember all the combinations. I don't even have to remember how to count in binary. I just have to go 0, 1, 0, 1, 0, 1, 0, 1, then 0, 0, 1, 1, 0, 0, 1, 1, and then 4 zeros and 4 ones. That's an interesting relationship. 1, 2, 4. Anybody describe that relationship? Is that 2 to the n? Right? 2 to the nth power, 1, 2, 4. If I have a 4-input truth table, A, B, C, D. Same thing, right? My far right column would be 0, 1. Oh, but you know what? Like, how do I know how many rows to do? This guy had 4 rows. And this guy had 8 rows. How many rows do you think this is going to have?
16.
16. You're right. 4, 8, 16. An interesting relationship. 4, 8, 16. How might you describe that relationship? 2 to the n. There it is again. All right. So I got 16 rows. So 0, 1, that's 2. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And then 4 zeros, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. How many zeros in column A do you think? 1, 2, 4. How many?
8.
8. You got it. 2 to the n. So I have 8 zeros over here. 1, 2, 3, 4, 5, 6, 7, 8. And then 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. So first of all, it's easier than trying to freaking get every single combination. And that puts it in perfect binary order. Every kid in your class is going to have this in the exact same order. When you're checking output columns to see if the kid's on the right track, you're not going to have to worry about like, wait, they put this row up here and they put this row down here. No, it's all going to be in this order. I'm not a stickler on a lot of things. It's one of those things.
Question. So if you wanted to write that down in binary code, do you flip it like a tree? So it'd be 1, 0, 1, like you would start from the bottom, go up then, or no?
Well, that would be
Your
counting
answer-
down. So like this is 15. This is
Okay.
14, 13, 12. That's how you count. Okay. So what do I do with this? I have a truth table. Okay. So your client, your design that you need to do is what fills out the output column, right? For each of these, you have some output and it tells us, okay, given these inputs, what should I do? No matter what circuit I'm talking about, the truth table always starts the same way, right? This is non-negotiable. This is always what it is. If I have 2 inputs, 3 inputs, 4 inputs, etc. What changes is the Z column, my output column. That's what's going to be different from circuit to circuit to circuit to circuit. So I'm going to put some baloney in here. I'm just going to make some stuff up. So I'm going to say over here, 1, 0, 0, 1. Okay. I don't know what design or circuit this is. And frankly, who cares? Some design needs it so that when A and B are both 0, the output's a 1. And if A and B are both 1, the output's a 1. Who cares? That's what needs to happen. Okay. So here's what we do with this information, folks. We're going to take this and we're going to grab what they call min terms. Min terms. And I like to say that a min term is a condition that will give me a 1. What are the conditions that will give me a 1 output? Okay, so the first condition that gives me a 1 output is this first row. And what it's saying is that A is 0 and B is 0. Ooh, and. So really it's not A and not B. So if we recall, and is multiplying, and not, we put a bar over it. So this would be not A and not B. Not A, a bar over it, and, so multiplied, not B. So if A and B are both 0, the output should be a 1. That's what this little expression here says. That's what this min term says. Not A and not B. This one down here is the other way I can get a 1. A, because it's a 1, and B. A and B. These tell us when we should get a 1. We should get a 1 if A and B are both 0, and if A and B are both 1. So this is a condition that gives me a 1, or this is a condition that gives me a 1. Or. So what I do with this is I bring this down here and I say, okay, so Z is A naught and B naught, or, remember the symbol for an or is a plus, which is kind of weird, or A and B. This is what we call an unsimplified logic expression. This describes this truth table, this circuit. It says we want a circuit that outputs a 1 when A and B are both 0, or A and B are both 1. It's a mathematical way of saying what we have up here. Okay. I'm going to throw some random 1s and 0s in this chart, and then I want you guys to see if you can figure out what those min terms would be. Just underlining so it's easier to see where they line up. So take a minute or two if you're still in here with us and see if you can figure out what those min terms would be. There's 3 1s. So there should be 3 min terms. Okay, so I'd say, where are there 1s? Here's a 1 right here. So A is 0. So that'd be A naught. And B is a 1. So that would be and B. And C is a 0. So it would be C naught. A naught and B and C naught.
Hey, Mike, does it matter if you do ABC or ACB on that?
It does not. It does not matter. I tend to keep it in alphabetical order, again, just so like terms look the same, but it doesn't matter.
But you don't have to group the knots together or anything like that?
No. So this one down here, A is a 1. So it would just be A. B is a 0. So B naught. And C is a 1. So be C. So A, B naught, C. And this last one is A, B, C. These are all 1. So we'd bring it into a logic expression. I just bring these 3 min terms down here. A naught, B, C naught. Or A, B naught, C. Or A, B, C. Last thing I need to say about this, I think, is of course we can go the other direction. So if I asked you, like for this far right one, if I told you, hey, I got A naught, B naught, C, D, where does that go in the truth table? So that would be 0, 0, 1, 1. So I go up in the truth table. Let's see. All right, where's that? Okay, so that's 0, 0, 1. Okay, so that means there'd be a 1 in that column, that row, rather. That's what that corresponds to. The other thing you'll see in the activity is they might say something like, hey, you know what else? What about BCD? What would you do with BCD? What it's saying here is that I don't care about A. A could be a 0. A could be a 1. I don't care. So I'd look up here in my rows and I'd say, where is B1, C1, and D1? When's B, C, and D1? Well, here. And here. So this actually corresponds to 2 rows in the truth table. So 211, what you guys are going to do in the It's Your Turn section, is practice on this. Practice, practice, practice. Lots of truth tables, lots of logic expressions. And I'll just tell you, it's a little unclear in the It's Your Turn what it wants in terms of like turn in, but I call this one, I would say, is like a complete understanding. Like try some of the problems. When you feel like you have a really good handle on it, you can stop. You don't have to do everything ever. You feel like you really understand it, you're good. Okay. But there's lots of practice in there so you can kind of get an idea. This is a good spot if you want to check that answer key. You know, if you want to look at the 211 answer key to make sure that you're on the right track, if you're not sure if you're pulling the correct answers down. Okay. Any questions on exactly this? Okay. I'm going to stop the recording then.